Hi everyone, I am Sergio Casas and today I'll be presenting our work on spatially aware graph neural networks for motion forecasting. In order to plan a safe maneuver, a self-driving vehicle needs to first understand the map topology and traffic rules. However, since there might be dynamic objects, it also needs to understand the free space and the occupied one, now and into the future. We can achieve this level of understanding from sensor data in two steps. We can run an object detector to tell us about the occupied and free space at the current time step, and then we can reason about how the future might unroll on a per actor basis by predicting their future trajectories and adapting the plan to respect other actors. Despite its difficulty, there have been many success stories in motion forecasting. Previous works have proposed efficient ways to encode a history of LiDAR point clouds and high-definition maps using convolutional neural networks. Modeling uncertainty independently per actor has also been well studied, including the understanding of multimodal behaviors. Finally, previous works have also shown how to optimize perception and prediction jointly. However, there are still challenges. Despite the importance of the interactions between actors in the decision-making of human drivers, current approaches make limited use of it. On the one hand, methods that do independent predictions per actor are blind to social interactions, and on the other hand, autoregressive formulations of the joint distribution over actors are slow due to sequential sampling. Let me try to convince you on why we should be modeling interactions. In this scene, we can see two cars reaching an intersection with no evidence of any of them braking. If we have a model that just looks at the local road topology and the past motion of each actor independently, the most likely prediction is just the extrapolation of previous motion, ending in a collision despite our belief of this event to be highly unlikely. The idea of this paper is to take into account the relative locations, speeds, and the context of the intersection when predicting. This is achieved by exchanging information between actors to make more informed inferences, such as predicting that the car on the left would most likely yield. Let's get started with our method. Our model takes as input several sweeps of voxelized LiDAR and a raster map in bird's eye view, performs convolutions on both input modalities, and fuses their features. Once we have rich features from the whole scene, we can obtain object detections, shown in red. Let's focus on one of the vehicles for now. Since we know the information ahead and to the sides is the most relevant, we attribute this region of interest to the actor. Then we can pull the features on that region as the summary of the actor characteristics, and we can do this process for all other vehicles in parallel. We can now further process the features with a CNN with global pooling and obtain a feature vector for each actor. Finally, we can connect them in an interaction graph, propagate their features through neighboring actors, and finally predict socially consistent marginal Gaussian distributions over future trajectories. Before diving into the details of our relational model, let me do a quick tutorial on graph neural networks. Each node in the graph has a feature vector as state. Let's focus on one of the nodes for now and see how can we update its states with information from its neighbors. For each incoming edge, we can compute a message conditioned on the sender and receiver node states, which have fixed size. We can then aggregate the message from the neighbors in a summarized message. And finally, update the node state based on the previous state and the newly aggregated message. I have just shown the message passing algorithm for one node and one propagation, but this can be performed efficiently for all nodes in parallel since it doesn't impose any ordering at the node or edge level. In our case, each node is in the directed graph corresponds to an actor. The initial node states are composed of ROI pooled features and spatial information such as the location, dimension, and heading of the vehicle. Based on this spatial information, each actor has its own coordinate system, shown in the diagram, defined by its centroid and heading, in which the motion forecasts are predicted to reduce the variance of the output since vehicles often go straight. The message function is parameterized by an MLP that is shared across all edges. Experimentally, we found that transforming the spatial information of the sender node into the receiver node coordinate frame is very important. We use max pooling across neighbors as our permutation invariant aggregation function, and we update the node states with a GRU cell where the previous node features are used as hidden state and the aggregated message as input. Two advantages of this model over previous approaches is that the model size does not depend on the number of actors, which changes from scene to scene, and that the final predictions do not depend on any ordering defined on the actors. Our model is fully differentiable and can be trained end-to-end through backpropagation using a multitask objective. A cross-entropy loss applied to the detection scores, a smoother one applied to the bounding box regression targets, and a Gaussian negative log likelihood applied to each waypoint of the motion forecast. We show the gradient flow in the dashed red arrows. We evaluate our approach in our challenging ATG4D dataset. This dataset contains over 1 million frames from more than 5,000 snippets collected across multiple cities in North America. It provides point clouds from a 64-beam LiDAR sensor and high-definition maps. It contains challenging urban scenes with many actors, making it interesting for interactions. First, we compare our approach against other perception and prediction methods, Fast and Furious, Internet, and Neural Motion Planner. We show the standard precision recall curves for vehicle detection and its associated MAP, where our method outperforms the baselines thanks to improvements in the backbone network. Let's now look at prediction metrics for a future horizon of 3 seconds. Our model achieves a substantial improvement in final displacement error at 3 seconds. However, this does not directly reflect the interaction understanding in our predictions, which is the focus of our spatially aware graph neural network. Therefore, we propose using the collision rate amongst the predictions to showcase the interaction understanding, with lower being better, since we know that in our dataset there are no collisions. Previous PMP methods did not model interactions explicitly, which explained our huge reduction in collision rate. Next, we compare against tracking-based approaches that do model interactions through social pooling layers and attention mechanisms. We benchmark against social LSTM, convolutional social pooling, and CARNet. We use an unscented Kalman filter and Hungarian matching on top of our object detector for a fair comparison. We can see that the gap between these methods and joint perception and prediction approaches is large, partly due to the difficulty of dealing with noise in the tracks. To mitigate confounding factors, we replace the past trajectory encoder of these methods by our feature extraction network and train them end-to-end. This allows us to directly compare the interaction operators proposed in these models, since they all use the same backbone and upper parametrization. We can see that our approach outperforms social pooling and attention mechanisms. In this ablation, we show that the previously proposed single-stage architecture for joint perception and prediction can be highly improved by using rotated ROI align on the detections and performing prediction as a second stage. Finally, we compare the performance of using no spatial information in the GNN message passing, using information in global coordinate frame, as well as in relative coordinate frame. We can see that using information in relative is particularly important for social understanding, reducing the collision rate to under 1 every 1,000. We compare our method qualitatively against the best performing baselines in a challenging scenario. The ground truth trajectories are shown in gray, while the Gaussian predictions are shown in a color map ranging from blue at the current time step to pink at 3 seconds. We highlight collisions with a red circle, and we can see that our model is the only one that produces a socially consistent prediction. In conclusion, we proposed a single model that can reason jointly about detection and relational behavior forecasting, taking into account interactions between actors. We designed a spatially aware graph neural network to refine probabilistic estimates of future trajectories, providing uncertainty. This approach is very efficient and in practice only requires 1 parallel round of message passing, in contrast to the sequential sampling of autoregressive methods. We have shown significant improvements with respect to previous methods across detection, prediction, but most importantly, interaction metrics. We would like to highlight that our model was able to cut down the collision rate by an order of magnitude with respect to the previous state-of-the-art methods in joint perception and prediction. However, the work I just presented has a limitation on the unimodality of the predictions and the difficulty of the motion forecast to follow the map. To tackle this, we extend SpAGNN to predict a mixture of Gaussian trajectories and propose a framework to add non-differentiable prior knowledge to make the predictions more precise and map-aware. Another subtle shortcoming is that SpAGNN only provides marginal distribution per actors. While this is not a problem for traditional planners that plan on the expected case, it can be a blocker for future research in motion planning that try to reason separately about different scene and roles. To remedy this, we propose an implicit latent variable model that can predict scene-consistent samples. Feel free to check them out. They are on arXiv now. Thanks for watching.